buddy, if you're out there.
Hello.
Hello. I need to open up my chat. I just remembered. So I can see what all you lovely people want to say to us.
Yeah. Well, how's it going, Kip?
Dude, it's going all right. How are
How
you
are you
doing,
doing?
dude? You doing good?
I'm doing good, yeah. Um, just excited to talk about momentum. That's a good topic.
Yeah, it is.
Yeah,
Dude, I'm gonna look us up on Twitch real quick. Make sure. Dude, can you see us on Twitch?
I did see us on Twitch, yeah.
Cool. Cool, cool. Well,
Yeah,
alrighty. So,
okay.
Jaden, as we can see from our slide, tonight we're going to be doing or talking about momentum and center of mass, probably some impulse,
Right,
as well as maybe some more integrals. Not positive about that last part, but we'll see.
right. Um, well, the integrals, we're gonna teach on just a little thing with the coefficients,
Oh,
right?
right.
But we'll get to that. We'll get to that in a little bit.
Okay.
Uh, so, Kip, before we jump into momentum, I think we better do a little bit of
Did
review.
you think? Um,
Yeah, maybe tell everybody what we did last time, then actually get into some review questions. Uh, how does that sound?
dude, that sounds great.
Yeah. So what did we talk about last time? It was we talked about Newton,
Dude, who's Newton?
right, and some of his laws. He was a he was a guy that figured out some things before other people did, and now he's very famous because of his mainly because of his three laws, right?
Uh huh.
It's laws of motion. Uh, talks about force. But anyways, we did that. Talked about force. Did a little bit of derivatives. So I guess that kind of leads us into our first review question. Uh, you want to take that one, Kip?
Sure. What is Newton's second law? Not his first, not his third, but his second. For any of you guys watching out
Yeah.
there, I'd love to hear what you know. So if you want to comment away and let us know what you guys think Newton's second law is, that'd be awesome. And you'll get
Yeah.
bonus points if you can name all three of them. Ooh.
Ooh, bonus.
We've got a comment saying, I don't think you're streaming on YouTube right now. I believe we are.
We are.
It's
You have to go to our page. There
Yeah,
was.
there was a technical error on the YouTube side of things. So it's streaming now, but it's not on the original link that was there. So that's our bad, and we're sorry about that. But in the future, that won't happen again. Trying to stream to two places at once
Yeah.
can be a little tricky sometimes. So, anyways, uh, um, alrighty. So Newton's second law. Since no one, I guess, really wants to know about Newton's laws, I'll just go ahead and answer it. It is mainly
Yeah.
this, right? Which is written as F equals um, ma. So force equals the mass times the acceleration, right?
Right.
Cool, cool. And
So what exactly does that mean?
Dude, it means the mass times the acceleration equals force.
Okay. I don't know. I just had like a weird like thought
Yeah, what was your weird thought?
about, dude. I just went like far in advance and was just thinking about light again. But anyways, we don't need that right
No,
now.
we don't. Um, Good. I'm glad you found it. Thank you for looking for it. Okay, so force equals mass times acceleration is Newton's second law, meaning that an object that is accelerating, right, times its
Right.
mass is how much force. So the bigger the mass, to get it to accelerate more, you need more of a force, right?
Okay.
So if Jaden weighed like 500 pounds, to get him accelerating, he'd need a much bigger force.
That'd be a big
Yeah,
Jaden.
it would, dude. Dude, you don't weigh that much?
Not on Earth.
Uh,
Maybe somewhere else.
Maybe somewhere else. Yeah, and actually, weight is a great example of a force, right? So,
Right.
if it's an interesting side fact, but when people weigh you in kilograms, they're actually weighing your mass, not weight by because weight by definition is an actual force, and they're actually just weighing your
Right.
mass. Alrighty, so that's cool that we now know it's Newton's second laws and we remember it. And by the end of tonight, we're actually going to be able to write Newton's second law a different way, which I guess has become more of the new conventional way to write Newton's second
Cool.
law. So that's kind of cool.
Cool. That is cool. Well, before we get into that, we got two more
Dude,
review
I know
questions.
I'm
Okay.
not jumping the gun, I promise.
Yeah. Uh, I wasn't
Dude, it sounded like it
claiming
sounded like you thought that I didn't
or
remember. We had more
claiming.
review.
Well, anyways, let's go to the second review question.
Whoa, dude, this one looks
Uh,
intense, man.
yeah. So it's one of our derivative uh, rules, right? We went over the product rule and the quotient rule. This is being multiplied, so it's going to be the product rule. So I guess let's start this,
Yeah,
shall we?
let's go ahead and start.
So if we remember, we have two functions, right? So that would be our f of x. This could be our g of x. And what the product rule says is we take the derivative of the first times the second plus the derivative of the second times the first. Okay? So the derivative of f, that would look like just a 3. Whee! That's a 3 if everyone knows and should. And then we have a g prime of x. Remember our little apostrophe thing here means prime. That means the derivative, first derivative. Okay, and that would be an 8x. Woo! So we have all of the functions that we need. We take the derivative of the first times the second. Whee! Just like that. Plus the derivative of the
Don't
second
mess up.
times the first. And then we can just do a little bit of multiplication, right? We can multiply the coefficient with that number there. We get a 12x squared plus, then we got 3 times 8, 24, and then x squared because there's now two of them. And this equals 36x squared. We can add the coefficient since we have the same degree on our variable.
Nice.
So that is the answer for that one.
Solved.
Solved. in the comments, ask questions if you didn't understand any of that, or if you figured it out before I did, let us know, because we want our smart students to be proud of
Yeah, we
themselves,
do.
right?
Should we move on to the next
Okay.
review now?
Yes, we should.
Okay.
Uh-oh, kid.
Uh-oh.
This looks
This one looks nasty, dude.
Dude, do you want to take this one, or do you want me to take
Dude,
this one?
I'll start, and you tell me if I'm doing something right or wrong.
Okay, I like this
Okay,
game.
dude. So the first thing I'm going to do is I'm going to find f prime of x.
Ooh, yeah,
I'm going to call
good
this
idea.
f of
Which
x.
one is F of X? Okay,
And I'm going to call this
cool.
g of x. So f prime of x is going to equal 2x plus 3. And then I'm going to say that
Nice.
g prime of x is going to equal here we go, 18x.
Whoa,
Dude, am I doing good so far?
that's awesome. Dude, you're doing great so
Okay,
far.
that's good.
But now, I guess it might be the hard
Yeah,
part now.
so
I don't know.
I'm going to do low, d high. So I'm going to do 9x squared times 2x plus 3
Awesome. I like
minus
what you're
high
doing so
d low. So we're going to do x squared plus 3x times.
Oh, we have a question
What?
real quick. How do you know what the prime is? How do you know what the first derivative of these functions are?
Well, Jaden, we have lots of videos that talk about it, but
Yeah.
thanks for asking the question. Um, so it's called the power rule, right? So the first derivative is why we say that's f prime. It's the same as saying first
Right.
derivative. What?
Yeah.
Yeah.
I was just saying it looks like a little one or
Yeah.
something, you know? Yeah.
And so we take the derivative of the top, and so we do that using the power rule. So we subtract 1 from the top exponent, right? But we multiply it by the exponent first. So you get 2x to the x squared minus 1, which equals
Right.
just 2x. And then you do it again to the second one here, and you just do 3x. So then you multiply, this is like saying this is to the first, so you multiply it by the 1, and so you just get 3x, but then you subtract 1 up here, so you get a 3x to the 1 minus 1, which is 0, and anything to the 0 power is just 1, so you get 3 times 1, which is 3. And then the same thing you do for the bottom one, so you just do 2 times 9, which is 18, and subtract 1 from 2, so you get 18x.
Okay.
But thank you for the question.
Cool.
So we got x squared plus 3x, and then so we got high d low, and now we got low d high. So wait, did I do something wrong? Is
No.
it high d low or low d high first?
Low D high minus high D low.
High d low. Okay. All right, so then we got 18x, and then it's all over low squared. So 9x squared squared, like that. Right, Jaden? How am I doing?
You're doing great, Kip.
Cool, cool. So now I'm going to go ahead and simplify this. So we're going to multiply this 9x squared into both of these, right? And so then we get 9x or 18x cubed plus 27x squared. And then we're going to minus, and we're going to multiply this to that and this to that. So we get minus 18.
Wait, what's this x here, Kip?
Dude,
18x to the...
What? Oh, that's supposed to be to a 3, dude.
Oh, okay.
Thanks.
Dude, you're just keeping me on my toes.
Yeah, I am. So then we got 18, so we got 18x cubed, and then we've got 18 times 3 is 36. No, it's 44.
54.
54. Thanks.
Yeah, you're welcome.
And it's going to be a minus because we're going to bring in the minus from out front to both, right, Jaden? So we got 54x squared, and then this is all going to be over 18x to the 4th.
It's squared, not multiplied by 2. So I think you just wrote it backwards.
Yeah, that's all I did, dude. It was... Thanks, man. Good thing you're here to help me out. Okay, so this 18x cubed will cancel with this 18x cubed, right? Whoa! That's
cool.
And then we've got this 27, and that's a 54, so that's just going to be half, right? So we're going to get a negative 27x squared.
Wait, is that half? Oh my gosh, that is half.
Over 81x to the 4th. We can cancel out some of these x's. Boop. And then we can divide these both by 9. So we get... Oh, wait, we can... Can we divide them by even bigger? Can we divide them...
By 27?
Yeah. We can divide them both by 27. So we get negative 1 over 3x squared.
Whoa.
And that is solved. Thanks to a little help from Jaden.
Yeah, you did great.
Thanks. You got like the answer sheet somewhere so we can...
Dude, no, I don't think we need an answer sheet.
You don't think so? That just simplified a lot. I'm just amazed at how pretty that got.
Dude, it's because this is math. Math magical. That's
Dude, do you think it's mathematical? Dude, I agree.
Yeah.
Rude.
All right.
Okay. So
we go on to our next little thing, I guess. It's a little thing with integrals. And Kip, we could probably stay on the Jamboard for this one.
On that. Yeah.
So, a coefficient. Let's first talk about what a coefficient is.
Jaden, what's a coefficient?
Some people might already know, some people might not. But anyways, a coefficient is this number in front of the variable, right? It's a number times a variable. That is your coefficient. Okay, the number there, that's a coefficient. And the cool thing about coefficients when you're integrating is we can just say, hey, go out here, go out front, and just hang out there until I take this integral, and then you can multiply by it.
Wow, that's so nice.
So that's cool. So we can rewrite this integral as a 3 multiplied by our integral of x cubed dx. And guess what, Kip?
What, Jaden?
We know how to take the integral of an x cubed. Right? That's part of our power rules with integration. So this equals, we still need this 3 out here, but it's going to be times x to the 4th, right? When integrating, we go up an exponent, and then we divide by that same exponent. And then we have this plus see
So we
here.
have a really good question that says, would you ever have more than one coefficient? And the answer is what?
I said, yeah, good
Yeah,
question.
the answer.
You can
I
have
mean, technically
you can
no,
have multiple coefficients like
but
this. Both of these would be considered coefficients, right?
right. But you would never have more than one coefficient in front of
Right.
a single, um, I guess, term, because yeah. So like 3x. So we've got like 3x to the third times 2 dx. So the reason why is if you have 3x cubed times 2 dx, then all you can multiply this 2 to the 3 and get 6x cubed dx. Right, Jaden?
Right. Yeah, if those are multiplied together, that's what you would get. In this situation over here, with integration, it would look like this, right? You'd have parenthesis, parenthesis, dx on the outside. You can multiply dx into both of these. Okay. So we would get like a integral, woo, that's going to be small, 3x squared dx. It's not right small and it's not going too well. Then you would plus, and we would have another integral, 2x dx.
Right.
And then we would just pull the coefficient out on both of these. So that's what you would happen if you had multiple term like polynomial.
Right. And you can,
Does that make sense?
yeah, and also you can only do what Jaden's saying about splitting the two integrals only if they are addition, right? So if you have multiplication, you can't split them into,
Addition or
yeah, addition or subtraction. Um, and then, yeah, Jaden, I realized I don't know if we ever talked very much in depth about what that dx term actually means. I mean, we did a little bit, but maybe it'd be a good review for people to know why there's that
yeah.
random dx at the end, because I just realized that I don't know how much we covered that.
So the dx represents a really, really small change in x. Okay. And that's meaning uh, if you have a curve, right? So some function that's graphed, what an integral represents is the area under that curve. Okay. And a really small change in x means so the x-axis is going to be our horizontal, right? So a really small change in x, that means we're taking all these really, really small changes of x, adding them together to get this area, right? We're just taking a whole bunch of, it could be rectangles, trapezoids, whatever, but what the integration represents is this, it's basically an infinite number of these really, really small changes of x to get the whole area.
Right.
Uh,
And so, yeah, thanks. I totally agree with you, Jane. The one extra thing I would add is that if we remember this right
yeah.
here, this 3x. Oh, dude, I'm using a black marker. Ew. This 3x is, or 3x
Uh-huh.
cubed is like our height, right? And then this dx is kind of like the width of our rectangle. And so you're
Right.
multiplying those together to get an area, essentially. And so we got another question. It says, why can you do that with addition and subtraction? Do you want to take that, or do you want me to take that?
Um,
Like as far as breaking up the integral goes into different parts.
so with addition and subtraction, uh, you can break it up like this because it doesn't actually change what you're doing, right? But if you were to break up a multiplication and then integrate it, then multiply it back together, it just changes the whole problem.
Right.
But with adding or subtracting, uh, it won't actually change anything
Yeah.
and the end result. I don't. You can add what you want.
Yeah,
It
I think the other thing to remember is that an integral of in and of itself by definition is a summation, right? And so if you have a summation and then another summation, you're not, like you said, you're not changing anything, right? So if I said, like,
right.
if I had 2 plus 3 plus 4 plus 5, I could do 2 plus 3 separately and 5 plus, or 4 plus 5 separately. So you would get, um, 5 plus 9, right? And then you would add those
Uh,
together and you'd get 14. And that would be no different than if you were to just add all those terms together in order, right?
that'd be the associativity property of addition.
Right.
Right. You can move around these parentheses as much as you want, but the end result will always be the same. But that doesn't always work with like multiplying and dividing, and that's why we have the uh, what's that called? Top of my head. Order of
Yeah.
operations.
There you go.
That's what it is.
And
That's why.
yeah.
Yeah.
And so it's the reason why we can actually pull these coefficients out front of an integral. If you remember from algebra classes, if you had like 3x plus 3x, right? And you had these in parentheses, you could pull that 3 out and say 3 times x plus x. And so it's that same kind of, it's the properties of addition that allow you to pull that 3 out front because it is a summation of all these different terms.
That's a good question.
Yeah. Thank you for asking. Cool.
So I guess to just end this coefficients, right? Talk about we can bring out the coefficient in front of the integral. Our last little step here, we just multiply it throughout. And because c is a constant, multiplying it by another constant would just make it a different constant. So you can kind of just keep the c as it is. But we'd get 3x to the fourth divided by 4 plus c.
Yeah. And that kind of goes with what, Kelsey's question was about, can you have two coefficients, right? C is technically kind of like a coefficient. I mean, it's a constant, right? And we don't know exactly what it is,
Right.
but 3 times C will equal a new C, but we can just write it as C because we know it's just going to be a number.
Right.
So
you could rewrite it as k because you want to differentiate them, but there's no point in doing that.
Yeah.
Because it's just a constant.
Cool.
All right.
All right. Should we keep moving, dude? Keep plugging along?
Yeah. Let's do it.
All right. So we've done some review, we've done some little bit of calculus, and now we're on to something called momentum. So, what on earth is momentum, Jaden? Let's talk about
Dude,
it.
I don't know. I've heard of people using that word like, "Hey, I can't stop now. I got to keep my momentum going."
Yeah.
Is that gonna be like the physics way,
It's going to
or
be similar. Yeah, absolutely. Or maybe you've heard about it when, people are talking about things like, wow, I don't know, they'll say that had so much momentum, right? And so it's like this interesting thing where we use it in English actually a lot, kind of like we talk about forces a lot in English. Um, but we use this word momentum in our day-to-day lives to describe things outside the realm of physics but are
uh,
actually based in physics. And the interesting part is people use those terms correctly, right? But they probably have no idea why they're saying that and what it
Right.
actually means that something has momentum, and why, if something has momentum, why it's harder for that thing to maybe stop moving. And so it's, anyways, we'll get into that. But for now, let's talk about what momentum is. So momentum is essentially the integral of mass times acceleration with respect to time, right? So remember that dt means a really small change in time. So Jaden, I'm going to go ahead and write something fancy here. And I'm going to say that we've got, so I'm going to go ahead and say that, we're going to be able to pull our mass out front, right? Because our mass is going to be the coefficient of acceleration, all right? Because,
Oh, I thought we went over that new
oh,
integral. Whoa.
dude, whoa, that's weird. It's like we planned
That's
that.
so
And
weird.
the reason why we're calling the mass the coefficient is because the mass of a system very, very rarely changes, right? Like, unless you somehow take something out of it or you convert that mass from mass to energy or something, that mass is probably going to stay in that system. And so that mass is just going to be a number, right? And so we're going to call it a coefficient. So we can go ahead and write this as mass and then the integral of a dt. Now, for those of you guys who have watched our class in the past, might realize something oddly familiar about this integral, this a dt, which when
Right.
we integrate out, we get the integral, or we get it equals, this equals mass times at. Now, if we remember from plus a c, we'll throw a c out here, okay? Now, if we remember from way back, a few lessons ago, we actually solved this integral of a dt, and we remembered that that equals velocity. So this whole chunk right here will
What?
give us a velocity, right? So
Oh, wait.
we can write that p, which p stands for the momentum, okay? I don't know why they use p, probably because
Do you know why that is?
I used to know, I think, but I don't remember anymore. Um,
So it's different words or something? I don't
yeah,
know.
I don't remember exactly. I do know that I mean, they're not using m, right? Because we've already got mass as m. So I
Right.
don't know if they just ran out of letters or what, but I'm sure that there's normally a much
Okay.
more scientific reasoning behind the letters that they choose. But P stands for momentum. Momentum. All right. So momentum. So we've got mass, and remember that whole second chunk is going to equal velocity. So the momentum of an object is just simply the mass times the velocity of that object. So that's
Wow.
interesting, right?
Yeah, I
You
see.
think? So what does that
Yeah.
mean? So Jaden, that means if I'm in a car moving 60 miles an hour, I can times it by the mass of that car and I will know the momentum, right? So the faster you're going, the more momentum you have, and the more
Okay.
mass you have, the more momentum you have. So something that's going really slow but has a really big mass could have the same momentum as something that's moving really fast and has a really slow, or has a really small mass, right? So like a snail and an elephant could have the same momentum if that snail was getting like shot out of a cannon, maybe, or something.
Yeah.
Okay.
So, okay, that kind of reminds me, last lesson we talked about the force,
Right.
right? And Newton's third law says that things, like when hit together, feel the same force, right?
Right.
Um, but they have different momentums because one object is more massive than the other. And that's why we, like, for example, when we drive a car and we hit a bug on our windshield, that's why the bug goes splat, because the car has a lot more momentum than that bug, right?
Right.
But they feel the same force. Okay, this is all just coming
Yeah,
together,
it is,
Kip.
man.
This is
So,
this
the
is
next
awesome.
thing that has to do with momentum is this idea of momentum being conserved in a closed system. Now, what on earth does that mean? Because that's a lot of, fancy words in one little statement there. And we got some fancy little funky, equation written out there that's maybe a little confusing for some people. But it's really quite simple. All it means is the total momentum PT equals the summation of all the momentums. Okay? So, for example, Jaden, and when it means by it's in a closed system, that means, let's say we're out in outer space or somewhere where nothing else is affecting us, really, right? So, me and Jaden are going to be floating out in outer space here. Boop. Dude, that's me.
Nice.
And here's Jaden over here. Sup, dude? That's Jaden. He gets a face. Okay. So, Jaden, I'm going to be moving this way. Okay. And I'm going to have a mass and a velocity. So, I've got a momentum and I'm moving that away. Okay.
Right.
Jaden has a mass and a velocity. And he's moving the opposite way of me. So we're floating away in space, okay, with our velocities. All right. And I was kind because I don't want to, say who's skinnier, me or Jaden, because, we know the answer to that. But so I'm going to say we have equal mass. Okay.
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 Sounds good. I like that.
So we have equal mass, Jaden, and we have equal velocities. All right. And if we remember back from way back when we talked about vectors as well, there's a direction associated with the velocity, and there's also a direction associated with momentum. So if we wanted to what?
Okay.
Yeah.
Momentum
is a vector.
Cool.
And the reason why it's a vector is because mass is what we call a scalar, right? It doesn't have a direction. But if you times a scalar times a vector, you still get a vector, right? And because velocity is a vector, then we still get a vector.
Okay.
Is mass always measured in grams/kilograms and such? Yes, it normally is, especially when you're talking about things in science classes. Jaden, what is the measurement of mass in United States measurements? Do you know?
I think kilograms is the SI unit.
But in the United States.
I think we also for mass use kilograms, but no one ever talks about kilograms. They usually do like pounds.
Yeah.
But that's not a mass.
That's a weight. So yeah, I guess maybe ounces? No, because that's still a weight.
Yeah, that's a weight.
Yeah, I don't think the US ever uses mass because we're weird. But
yeah, unless you're in the scientific community.
But good question. All right, so me and Jaden have the same momentum, right? Doctors use kilograms, yes, because they're smart and they only care about your mass. They don't care about your weight. All right, so
yeah, there's no reason.
Yeah, because I guess wanting to know how much of you there is, using mass as a better unit than weight. All right, so in this case, but when the doctor says we're gonna take your weight or how much you weigh, they don't know what they're talking about. All right, but back to this. So we have P1, right, is equal to negative, because I'm going to say to the left is negative, because you remember we can choose whatever we want to be negative. And this is P1.
Right.
which is me, and then to the right is going to be P2, which is Jaden, and that's going to equal a positive MV. So we have two momentums, right? And we can sum those momentums together and to get the momentum of this entire system, right? So if we put a blob around me and Jaden, then that's that system, right? So in that case, our total momentum, because they're opposites, PT would actually equal 0. Okay?
Assuming we have the same
I
mass and same velocity.
Right. Yeah.
Okay.
So P1 and P2 are the same in this case. All right. Now, truth be told, Jaden probably, has less mass than me, so he'd have to go a little bit faster than me to make this truly equal 0. But that's okay. We're dealing with physics. Now, if we were both going the same way, right, it would be 2 MV, and just depending, things would kind of change around a bit. We could add more people to the system. And yeah, that would kind of, alter how this all works out. Okay, so we've learned a little bit about momentum. Now we're going to go on. I guess there's one more thing that I want to talk about as far as momentum is concerned. Well, I guess we'll talk about that in a second. We'll talk about that when we get to impulses in a second here. Okay, so moving on. Oh, wait, we're doing impulses next. Wow, look at that. Whoa. Okay, so Jaden, if you remember from the last slide, momentum is conserved, right? When it's in an isolated system, it's the mass times the velocity. So if your velocity never changes, your momentum never changes. Well, what happens when you want a change in momentum? You have to apply an outside force onto an object, right? So let's say I'm floating in space here. Boop, boop. Look at me. Okay. And then Jaden, I guess, we're going to continue to talk about the conservation of momentum first, because it will make, there's something I did forget to add. So let's say that me and Jaden are hanging out and, wait a second, if kilograms aren't weight, then how do scales measure it? So scales measure it based on what they do know about force, because weight is force, right? And so they know the acceleration of gravity. And if you remember, we talked about, and this is a great segue into kind of this idea of opposite and equal reactions that I'm going to talk about here in a second, is that if you have a object that you're standing on, right, Jaden? That object pushes back up with the same force. And on the surface of the Earth, we have an acceleration due to gravity, and so it can actually feel that force. It measures that force and then can just simply divide by the acceleration of gravity to get your mass. I'm assuming that's how scales work.
Yeah, that sounds good.
But yeah. Okay.
I don't know how else
yeah.
I would.
And so that's why I think we normally do weigh things, right? Instead of just getting kilograms, because anyways, it's because we can more easily find weight than we can a mass. All right. So back to this. I got me chilling out here in space. I'm not going to have Jaden here, okay? Well, actually, I'm going to have Jaden. And Jaden's over here. And in this case, I'm chilling, okay? We're both standing still, floating in space. But Jaden, I want to come over to you, okay? So we're in space, though, Jaden. This is a problem, because when you're in space, there's no friction, there's no anything, right? No matter how I try to move, I'm just going to stay in the same spot. Why? Because there isn't an equal and opposite force for me to push off and move. Okay?
That makes sense.
But Jaden, I was smart enough to bring my lucky rock with me, my moon rock, to space with me. Okay?
Whoa,
And I'm like, Jaden, I
smart
want to come
guy.
see you. So what I could do is I could turn and face away from you, and I could throw this rock. Okay? So, according to physics, what we learned last week, if I throw that rock, there's going to be an equal and
Fire.
opposite reaction on me, right?
Right.
And so in that case,
The rock goes that way, you go toward me.
exactly.
That's pretty cool.
And so I'm going to go towards you, right? And now we've got a rock going the opposite direction and me going that way. The momentum of that
Uh-huh.
system still has to be conserved, right? And so the throwing of that rock, if I was to take the velocity right as soon as that rock left my hand, I'd be able to figure out how much momentum I would also have, because we have a rock going that way and I'm going that way, but the total momentum of that system still actually has to be zero, right?
Yes.
Because there was no external force, right? If I drew a bubble around us, nothing outside of there acted on us, which means that the
Right.
total sum of momentum between me and that rock still has to be zero, even though we're both moving now when we weren't moving before. So that's kind of a
So
crazy
you
thought.
would have different masses. So then you would also have different velocities, but the momentum would be the same.
Right.
That's
That's
cool.
pretty cool. So,
Dude, but what happens when you hit me?
dude, then at that point, we're technically still all an isolated system. Okay.
So it'd still have to be zero, huh?
Yeah. So
That's cool.
now between me and you, the total momentum would still have to be zero.
Okay. Nice.
Nice.
Okay, so what's this
Okay.
impulse?
So let's move on to impulse. Yeah,
Yeah.
because we're running a little low on time here, aren't we? All right. So, what on earth is an impulse? An impulse is a change in momentum. Okay. So, this looks awfully familiar to what we did in the previous slide to find momentum. But in
Yeah.
the last case, our v was constant, v wasn't changing, right? Now, in this case, our v is going to be changing because there's actually going to be an acceleration put into the system. A force is going to, even counting the rock, it would be zero. Yes, it would still be zero. The entire momentum of the system cannot change until an outside force acts upon it.
Axe.
Um, and so now, well, let me think about this for a second. I don't know if it would still be zero because I'm wondering if you would be outside.
No, it would
It would
be
still be zero, right?
yeah,
Yeah.
because you would bump into me, you would
Bump.
become still, and I would be
Right.
going the opposite way with all that
Right.
momentum. So it'd
It'd
be
still be zero.
the same as
Yeah. But now,
assuming you had mass and
yeah.
velocity.
But
Uh,
so when there's a change in force with the change in time, that's when an impulse happens. And so a good example of an impulse is, say, a crash. So let's say that, I run into something, right? There is a there is going to be an impulse. There's going to be a force that's impacted, um, that's going to slow things down, right? So, like,
So your acceleration would decrease if you ran into a wall. And at that point, we would get that change in momentum,
Right.
right? Okay. So this seems like it's going to be like the change of momentum happens really quickly with impulses, right? It's like right on the impact. That's when it all happens. Is that correct
Uh,
in thinking that?
yeah. I mean, that's in part, yeah, that's part of it. I'm just trying to think to, so the impulse is like the change. Normally, it's the change in momentum of a single object, right? That you're looking at. You're not looking at the momentum of a total system per se.
Uh,
Um, so, for example, me in this example, right? There's going to be an impulse on me when I throw that rock. The total
okay.
momentum of the system will stay the same, but my momentum changed, right? My momentum
Okay.
went from zero to something else. And that change in momentum can be found based on the acceleration, times the mass for a certain amount of time. Now, why on earth does this matter and why is this so important? Well, if you remember when we talked at the very beginning about momentum and people using it in all sorts of terminology and how if you have momentum, it's hard to slow it down and all this kind of stuff. Well, that's absolutely true, right? Because you're going to need a bigger force to slow something down that has a bigger momentum. Okay.
Okay.
Um, and so, this idea of momentum and forces working together is kind of this weird thing that people say interchangeably all the time, but isn't necessarily correct. Um, but the idea is if you can spread out the time, right? And so if you're spreading out the time, you're actually making the force smaller. This is really important for collisions, right? So if I'm in a car crash and I smack, my momentum is going to want to keep sending me forward, right? Now, as soon as I hit something in my car, all of a sudden, all my momentum is going to transfer from me to whatever I'm hitting, right? So, in the case of a car, the car has such a greater mass than me. When I hit that car, essentially the momentum of the whole system doesn't change, right? But my momentum is going to instantly go to zero, and the car's is barely going to you know it's barely going to have any speed associated with it because it's so massive. And so because I hit it, my momentum changes that quickly, right? And so I'm going from a velocity of 60 miles an hour to a velocity of 0 miles an hour in a matter of a second. And so my momentum changes rapidly. But if you throw in something like an airbag, now all of a sudden
Okay.
you have a longer time, right? Because there's a hard force, but it's not as hard as just hitting and stopping instantly. And now you have a force decelerating you because you have a longer distance, right? That you're pushing something
Right.
before you hit something quickly and stop. And so that's kind of the importance of momentum and impulses, and why they kind of it's an interesting kind of, I don't know how to explain it exactly, but it's how, you know, if you're in a car, really the thing that matters the most is how long your
Uh,
car, how much room of travel
yeah,
does
like
your
switch
body
guns.
have?
uh, so
So,
that's why you see in a lot of cars these days they have that like crumple zone in the front of their car plus the airbag, right?
right,
So if you were to just whack into a wall, you'd be dead. But because your car has that crumple zone and the airbag, you have that a little bit of time. It happens really fast, but it's still more time than zero time that you have to slow down.
right. And so you can actually
That's
calculate,
that's really
right, from this. Let's say you have your average, you have your momentum. Let's say that I went, you know, MV equals like, I don't know, 500, right? And let's say it went from
Uh-huh.
500 to 0 in zero point 0.2 seconds, right? You could actually solve for the force
Four. Four.
that was applied during that time, the average force. And so you can use that math, right, to figure out, okay, what, the average human can survive this great of a force. So then you can use this math of if I have this much momentum, what force, am I trying to get? And is it even physically possible?
Right.
And this is where, anyways, it's a really cool thing that's really actually quite simple math, but you can quickly solve to see if a person would survive a crash or not. So,
That's
dude, that
crazy.
is crazy.
Uh,
Dude, should we go into center of
you
mass
could
or should we wait till next week?
maybe wait till next week. I don't know.
But it fits in. Dude, I'm just going to start. I'm just going to go through it real quick. Okay?
Okay, that sounds good.
Okay. So, essentially, what the center of mass is of an object or a world of objects in an isolated system is you simply add all the masses together times their radius divided by the total mass. So it's kind of like a weighted average of the masses,
Okay.
right? And so why this follows the same rules as momentum is the center of mass, just as um, you know, the momentum doesn't change, the center of mass of a system cannot change unless there's an outside
Uh,
force acted upon it, right? So in the case of me throwing the rock and me traveling, the center of mass would still stay in that same spot. So if I'm here, boop, and I throw the rock this way, okay, the center of mass is going to stay in the same spot no matter how far away we travel. We could travel, 5 light years away, but
right.
our center of mass would still be in the same spot.
And you see this in like, I guess, solar systems,
Right.
right? Orbits. Uh, the Earth and the Moon has a center of mass that's not the center of the Earth because the Moon is far away, right? And you have a center of mass for our whole solar system that's not the exact center of our sun because there's all these other objects in the solar system that change it just a little bit. Uh, and like in binary star systems, you have center of mass where two stars are actually rotating around each other, but you can see that their orbits aren't just totally around one star.
Right.
Uh, but that's just a side
That
note.
is a cool side note. No, I like it. Thanks, Jaden. And I mean, it's mathematically intense, but you can calculate using these ideas of conservation of momentum and center of mass, right? That's like, these are all the things like that we do in a quite often and don't realize that they have this effect. One of them being like, let's say you're on a boat, right? Like a small kayak or something. And if you try to run to the front of the kayak actually moves backwards behind you as well. And this is the idea of conservation of momentum as well as the idea of conservation of, the center of mass, right? The center of the mass has to stay in the same spot. And so if you're running to the front of the boat to keep that center of mass in the same spot, the boat actually has to move backwards.
Yeah, very
And
cool.
that's why you can't move a boat by running on it back and forth. Like you can move it in the same spot, but you won't actually get anywhere.
Dude, that's like you just need a really long boat, and then you'd have your own
Yeah.
treadmill, right? You just be running back and forth.
And so that's why you need to get a paddle in the water or a motor or something, which applies an external force to the system to make you move forward.
Cool.
Cool, cool. Well, thank you guys all for watching. Tonight has been so math magical, and
This was a really cool couple of ideas that we went over tonight. I don't know. That's all I gotta say is it's just
it
cool.
is cool. It's kind of, I don't know. This one's just it's there's some math in there, but I just like the concepts, and so they're like these concepts that I feel like this is where you start to get to people trying to cheat physics a lot, and they try to come up with ideas on how to make magical things work that I don't know. You're so welcome. But
It doesn't serve the
yeah,
momentum and it falls apart
right.
right there.
Or yeah, you do get people thinking, it's like they'll try to move a boat in the water by rocking back and forth or something, right? And they're like, we can do it. We can get it going. It's like, no. You're never going anywhere. I promise. You're going to stay in that same spot. So,
Yeah. Well,
well,
that was
thanks for
awesome.
watching. Don't forget to like and subscribe if you haven't. And on Thursday night at the same time as this lesson, we will be doing our lovely homework live stream. So if you guys know anyone that needs any help, or if you need any help, please tune in on Thursday and we'll be here for you.
Yeah. Okay.